And we're back. Welcome back and happy Thursday. Today, we will switch gears with a new topic, namely support vector machines. And this is going to be a clever variation on our humble linear hypothesis. When we last left off, we talked about validation. And in that validation, we took our data set and we peeled away some number of those in-sample points, k many of them, to form our validation set. And this validation set carved out of our data set, leaving the resulting data set, something we call dtrain, our training data. Now, our validation set is of size k, and our training set is of size n minus k, where n was original data set size. And so now we have some number of hypothesis sets, different models, many of them, going from script h1 through script hm. Now, as we discussed, these could be, for example, different degree polynomials, and you're selecting as part of your training regime one of these models that gives you the best out of sample error estimate, or they could be all, say, degree 10 polynomial with different regularization parameters, lambda. So we have our limited data set, dtrain, and we use this dtrain with each one of our hypothesis sets. And because dtrain does not have the full data set, our final best hypothesis for each one of these hypothesis sets, H1 through HM, is going to be limited. So we term that G1 minus through Gm minus. Now, once we have our finalists, these G1 minus through Gm minus, we then run the validation set through each one of them, and we get an estimate of out-of-sample error, E1 for G1 minus, E2 for G2 minus, through EM for GM minus. And we use these estimates for out-of-sample error to pick the best hypothesis, the best performing limited final best hypothesis. And we're calling that our EM, which is the smallest or best out-of-sample error estimate associated with the mth hypothesis set. And once we get that mth hypothesis set, we then run learning again with the full data set that includes now taking our dtrain and adding back in those k-many in-sample points for dval into our data set. And then we use the full data set on that mth HM, that best hypothesis set associated with that best limited final best hypothesis that minimizes or has the smallest out-of-sample error estimate. And we take that HM star and we run learning again with, this time, the full data set to get our GM star. And so we tried to strike a balance between wanting to have this K big and wanting to have this K small with cross-validation. And we showed that cross-validation error is, in fact, an estimate of out-of-sample error. And we can use cross-validation to strike that balance between making K small, meaning we only have a validation set of size 1, and also making K big, we have a data set of size n minus 1 for dtrain. All right, so let's continue on to this idea that drives support vector machines, namely the max margin classifier. And so if we're finding a linear hypothesis that separates the points consistent with the labeling action of the unknown target function, there are many different choices we can have. This purple line in each of these choices is a perfectly valid hypothesis that produces the same assignment of labels as the target function. But which one of these is best? Well, if we think about the distance between the closest point to the hyperplane and that other amount, the so-called margin, there's an intuition that says, well, a bigger margin is better. But is a bigger margin better? Let's think about it. They all produce the same dichotomy that matches the unknown target function's labeling. But if we look and think about noise, what does noise do? It changes the values of your features. And if we change the value of features, for example, this red point might shift down here. And if it shifts a little bit, well, as a red point, it's now a misclassified example. But if we shift that same amount for a larger margin, well, it's still red and it's still correctly classified. And so a bigger margin can tolerate noise in your data better than a smaller margin can, even though it is able to produce the same dichotomy with in-sample error equal to 0. And so now what we're enterprising to do is not just find some hypothesis that minimizes in-sample error. We also strive to find a particular hypothesis, W, that also maximizes the margin. Now, of course, recall the growth function, and we use growth functions to collapse the infinite space of the hypothesis set based on combinatorial argument in terms of the dichotomies that this hypothesis can induce on a data set of size n, rather than considering all of the unique instantiations of our weight vector. And so here we list all the possible dichotomies, 8 of them, for a line on the plane, hyperplane in 2 dimensions, using a data set of size 3 points. Now, of course, if we were to include this idea of maximizing the margin, one of the things we do is we start to prune or decrease the size of the hypothesis set. And why is that? Well, let's take, for example, we have a margin that's this wide for this particular hypothesis. And what if we were to impose a constraint that your margin had to be bigger? Well, that would mean this hypothesis is eliminated from consideration. And this hypothesis is limited from consideration, so is this one, and so is this one. If we set a constraint, your model, your margin has to be this big. Now, of course, what that strives to do is it decreases the number of hypotheses that are candidate hypotheses for this particular learning algorithm. And as such, we're essentially decreasing the complexity of the hypothesis set, which is beneficial for a decreased VC dimension because you have fewer models. And we know that if you have a decreased VC dimension, the end result is you need fewer in-sample points in order to ensure that out-of-sample error tracks well with in-sample error as defined by Herfting's inequality, and specifically the VC bound, because that negative decaying exponential will more easily overpower a smaller, less complex model or smaller VC dimension model. And so the idea then is, how do we actually measure this idea of distance to the hyperplane, if that is going to be the criteria we employ for finding some good working hypothesis? So let's have some definitions here. Let's define xn to be the data point nearest the plane. Now, the plane is going to consist of all data points, x, such that W transpose x is equal to 0. So if you're on the plane, or on the line in 2 dimensions, W transpose x is equal to 0. Xn is that data point nearest to the plane, but not on the plane. So the question that we ask then is, if this idea of margin size is important, what is the distance of this point xn closest to the hyperplane? Because if we look back at these different candidate hyperplanes, we see that the points right on or closest to the hyperplane are the points in question that define the margin, and we want to maximize it. So we want to be able to measure the distance of these closest points to the hyperplane, i.e. the margin points, measure their distance to the hyperplane. So what is this distance of these xn nearest points to the plane? So let's make some additional convenience-based assumptions, because we want to make life easier for one another. Now, of course, if we have W transpose xn is going to result in some score, and that score is going to be greater than 0 in absolute value. Now, of course, if you are on the positive side of the hyperplane, your score is positive. If you're on the negative side of the hyperplane, your score is negative. And so certainly it's the case that if we take absolute value of this closest point, W transpose with its closest point, that's going to be greater than 0. Because we know it's not on the hyperplane, so it's either going to be positive or negative, i.e. different from 0. In absolute value, it's greater than 0. We know this for sure because by definition, our xn is not on the plane. It's nearest to the plane. And so the other thing that we can do is that we know it's greater than 0, and we can actually normalize W. We can take W and multiply it by a scalar, like 0.1 times W, and then take that transposed xn. And as such, we can shrink down or scale up that score. And we can do this relating W to the margin. And so if we multiply this hyperplane by a scalar, it doesn't change the plane. It just changes the score. And we can multiply by such a scalar, this hyperplane, such that W transpose xn, where xn is that closest point to the plane, in absolute value is equal to 1. And so if W transpose xn is equal to 1, and xn is the closest point on the plane, any point that's not closest to the plane is going to have this value, absolute value W transpose xn, is going to be greater than 1. Because by definition, we can scale W up and down specifically so that the closest point, xn, to the plane is such that W transpose xn is equal to 1 in absolute value. So now, we're going to do something a little bit different from what we've been doing all semester long. We're going to remove W naught, that dummy variable, from our W vector and just talk about W in its original form in D dimensions. And we're going to take our W naught and now call it B, the bias term. So now, going back to our definition of the hyperplane corresponds to all points X such that W transpose X, where W is in D dimensions, W transpose X plus B, the bias term, is equal to 0. And of course, we're assuming we also remove X naught from our X vector. So this is our definition of the plane, and we get it from this expression we started out with. It's just we're treating our W as being D-dimensional instead of D plus 1 dimensional, and we're also treating X as its original D-dimensional X vector. So the plane then becomes the set of points X such that W transpose X plus our bias term is exactly equal to 0. Okay, so we have two things. We have W transpose Xn in absolute is equal to 1. We have W transpose X plus B is equal to 0. All right, so let's look at this idea of the distance, how we measure this distance between our off-plane point, xn, that's closest to it, and the plane itself, W transpose X plus B, is equal to 1. Now, of course, if we're thinking about this W in D dimensions, then our point closest to the plane is going to be W transpose Xn plus B in absolute value is equal to 1. Now, this follows from the previous slide when we had that scaled up and down W vector. So if we can scale it up and down in its D-dimensional version, that's just W transpose Xn scaled up and down, our W, plus our bias term in absolute value is equal to 1. And so we have, for that off-plane point closest to the hyperplane, that Xn, we have W transpose Xn plus B in absolute value is equal to 1. And we know we can always scale up and scale down W with a scalar to make sure for the closest point to the hyperplane that this is the case. It's equal to 1. So let's imagine then we have 2 points, and we're going to make them arbitrary points without restriction. And these points are on the hyperplane. And let's call one of them X prime and the other X double prime. So here's our hyperplane. Okay, that's the hyperplane. And we have our X prime here. We have our X double prime. Now, we didn't set any restrictions on them, but we know because x prime and x double prime are on the hyperplane, by definition of what it means to be on the plane, we know that it's the case that W transpose x prime plus B is equal to 0, because x prime is on the hyperplane. And we also know that W transpose x double prime plus B is also equal to 0, because x double prime is on the hyperplane. Now, of course, we know on the right-hand side of equality, 0 is equal to 0. So if that's the case, we can equate these two equations. We can say W transpose x prime plus B is equal to W transpose x double prime plus B. And so if we take our expression and we subtract this W transpose x double prime from both sides of the equality, well, the B's are going to cancel, and we get W transpose x prime minus W transpose x double prime is equal to 0. And so we factor out the common W transpose. This is just unwinding the distribution of multiplication by W transpose from this subtraction. And we get this expression. We get W transpose x prime minus x double prime quantity is equal to 0. Now, of course, we didn't set any restriction on x prime and x double prime. So these could be any 2 points on the plane. And if we look at x prime minus x double prime, that forms a line. It's that line that we draw here where the tail starts at x double prime and the head ends at x prime. And because we didn't set any restriction on x prime and x double prime, this difference, x prime minus x double prime, refers to any vector, any line that you can draw on the plane. So it could be this line, it could be this line, it could be that line. Doesn't matter. There's no restriction. X prime and x double prime are free variables. And so it is the case now, if we take our W, we know that W transpose times any line on the plane, that's any line, is equal to 0. So what does that mean? It means that W transpose is orthogonal to any line on the plane. And because it's any line on the plane, W transpose is orthogonal to the plane itself. And so we know for a fact now that W is going to be orthogonal to the hyperplane. So we draw it that way. So now what we want to do is we want to measure the distance between our xn and the plane. And how we're going to do that is we're going to take any point on the plane, let's call that x, and we're going to take our closest point off plane, let's call that xn. It's going to be the closest point to the plane that's off the plane. And so now we can absolutely draw a vector between that on-plane point x and that off-plane point xn. And there's the vector. It's xn minus x. Now this vector leaves the plane because xn is off the plane. And so if we wanted to measure the distance between xn and the plane, that's just going to be the projection of xn in the direction of that w vector, which is orthogonal to the plane. That's this distance. Now, of course, what we want is not w, but we want the unit vector in the direction of w. So there's the unit vector in the direction of w, and w itself is that vector. And so what are we going to do? Well, if we want to project xn onto w, we can just take w, unit vector in the direction of w, transpose that inner product between that unit vector in the direction of w and that vector. So here's the vector that starts on the plane and goes off the plane. All right. So what actually is this unit vector in the direction of w? Well, we know that the weight vector is perpendicular to the plane, is w, and if we want the direction, we just divide w by its magnitude. And so w hat is equal to w divided by the magnitude of W. That's how you get a unit vector in the direction of W. All right, so now we take that inner product and we get W transpose times that quantity of xn minus x. And that's the distance that xn makes to the hyperplane. Is the distance of the closest point, because by our convention, xn is the closest off-plane point to the hyperplane. Okay, so now that being the case, let's actually compute this W hat transpose times xn minus x. So we have our W over magnitude of W, W over magnitude W, and we multiply that transpose times xn minus x. So we distribute that W transpose through that parenthesized quantity, and we get 1 upon the magnitude of W times W transpose xn minus W transpose x. Now, we're going to take the absolute value of this because we care about the magnitude, not the direction. We don't care if it's on the positive side or the negative side, so we're going to take in absolute value this distance. So now we're going to take this distance, and if we add 0 to this expression, plus 0, it doesn't change it mathematically. One way of saying plus 0 is by saying plus b and minus b. And if we do that, we'll group the plus b with the W transpose xn, and we group the minus b with the minus W transpose x. So we get the equivalent expression mathematically, doesn't change it from what we had as this distance. We have 1 upon the magnitude of W times W transpose xn plus b minus W transpose x minus b. Now, of course, we know that W transpose x plus b, if we negate it, we get this expression down below. Now, W transpose x plus b, we've seen this before. That is the definition of the hyperplane, and we know the hyperplane is all those points x such that W transpose x plus b is equal to 0. So this term, we can just call that 0. Now, this other first two terms, W transpose xn plus b, we've also seen that before. We said for the closest plane on the point, we can scale our hyperplane W up and down with a scalar, and we can do so such that for the closest point to the plane, off the plane, this W transpose xn plus b is equal to 1. So we're going to set that to 1, and we end up with 1 over magnitude W times 1, which is just 1 over magnitude W. And so this distance between our closest point off plane to the hyperplane is going to be 1 over magnitude of W. And that's the quantity that we want to maximize. We're trying to find the W, the hyperplane, that maximizes the margin to the closest point off the hyperplane, or closest point to the hyperplane. And so when we do this, we want to make sure that we maintain some constraints. And the constraint corresponds to this rescaling of the hyperplane such that for the closest point to the plane, that W transpose xn plus b is equal to 1. We still want to maintain that. Now remember, when we have this constraint about the closest point to the hyperplane, recall that the hyperplane in question, while we're trying to maximize the margin, it gets all of the labels correct. And so we can think of this constraint of minimizing or finding the in-sample point that's closest to the hyperplane. We're essentially saying get the classification or the labels correct, because that's essentially what this is doing, this rescaling such that the closest point is equal to 1 when we compute W transpose xn of that closest point plus b in absolute value. And the absolute value says that we don't care if it's on the positive side or if it's on the negative side of the hyperplane. Make sure that the closest one satisfies this constraint. Now, of course, this constraint presents us some problems. It's a maximization problem, so maximize the margin. Well, that's good because we know that large margins are more robust, less susceptible to noise. But we want to say subject to getting the classification correct for the closest off-plane point. Okay, well, this minimization presents us a problem. Why? Because for every single instantiation of W, we now have to check all of our n many data points finding the minimum. This minimum is a little bit troublesome for us, and that's going to make this a lot harder to compute. And so one of the things that we notice that if we have the classification correct, it is absolutely the case that we can drop the absolute value and get the same effect if we multiply the ground truth class label by this W transpose xn plus b, because this is effectively a score. Now this score, if we multiply yn times this W transpose xn plus b, well, we know in absolute value this is equal to 1. And so that means without the absolute value, this is either -1 if it's on the minus side of the line, or it's +1 if it's on the positive side of the line. So that being the case, if it is on the negative side of the line, yn is -1, minus times minus is plus. If it's on the positive side of the line, plus times plus is plus. So that's plus. And so we can achieve the same effect without this minimization by changing this constraint from a minimization to be subject to yn times our score W transpose xn plus b greater than equal to 1. Now, of course, this corresponds to both the closest point, and that's the one for which equality is achieved, but those points that are not the closest, that's when the greater than is going to be achieved. So this applies for all the data points without this minimization that is so troublesome. So now that we have a new version of this constraint, we can also perform some algebraic manipulation to change this maximization objective. And so one of the things we can do is, okay, we can take the reciprocal. If we take the reciprocal, that changes the maximization problem to an equivalent minimization problem, and that would be the minimization of 1 over magnitude of W. Now, of course, magnitude of W has a square term, and squaring has a square root, and squaring something is a monotonic transformation. So if we squared that, we would get W transpose W, and if we multiply by a scalar 1/2, that is also a monotonic transformation. So now we can change our expression of this optimization problem from the maximization of 1 over magnitude W to the minimization of 1/2 W transpose W, and it's the equivalent expression, the same optimizer, because monotonic transformations are order preserving. Now, the only difference is that when we take the reciprocal, the inverse, you change your maximization problem to a minimization problem. And we have our new constraint here, subject to getting the classifications correct, both for the closest off-plane point as well as those points that are off-plane that are not the closest, which corresponds to the greater than part of this inequality constraint. Okay, so let's take a look at the SVM formulation a little bit more closely. And so we have our minimization problem, and we have our new set of constraints. And these constraints are so-called inequality constraints, which presents us a little bit of a problem. We want to change this to make our lives easier. And this objective, it looks like a quadratic. So there are a lot of solvers that we can use for this quadratic programming, but we have this confounding inequality constraint. And so if we look at this, compare this to something that we've looked at in the past, this is very related to regularization. In regularization, we were optimizing by minimizing in-sample error, and we had this constraint on the soft budget, as it were, on the weights, W transpose W. With support vector machines, we're minimizing W transpose W, but our constraint is subject to all of the classifications being correct, which is the same as saying minimize in-sample error. Now, both of these ideas are going to blend together using the Lagrangian, and we'll talk about the Lagrangian in detail. But before that, this is the answer, and we'll kind of fill in the backstory about how we get to this expression. This expression is called the Lagrangian formulation. It's called the primal problem, and you notice here that we don't have any constraints. But what we do have is a new form of that yn times the score, and you notice here we subtracted 1. So we've taken that inequality constraint and we've recast it in terms of equality, but we've added this other variable, this Lagrange variable. So we take this expression and we're going to perform 2 operations. We're going to minimize this expression called the Lagrangian or the primal form with respect to W, a weight vector, and B, the bias term. And then once we get the solution from minimizing with respect to W and B, we're going to substitute those results back into the primal form, get a new formulation that we're going to maximize with respect to our Lagrange variables, our alpha n's. And so when we do this gradient with respect to W for this primal form, we get W, because this is like saying W squared, there's a 2, so that 1/2 goes away, so multiplied by 2. So we get W minus, and then the only term that involves a W is this term. We take that term, we have alpha n, yn, W transpose xn. And so we have W to the 1 power, that becomes alpha n, yn times xn, which is here. And we set that equal to 0 to solve for W, and then likewise, the derivative, the gradient with respect to the bias term B, we have a single term that involves B, alpha n, yn, B. So we're going to get our alpha n, yn times B to the 1. That's just alpha n, yn, and that's here. So let's look at how we get to this Lagrangian before we continue forward. And this Lagrangian is going to help us take this constrained optimization problem and convert it to an unconstrained optimization problem that we can solve through 2 steps, taking a minimization involving a gradient and a maximization with respect to alpha involving another operation. And so we have a minimization problem and a maximization problem. So here we have our original constraint that says get the classification correct. And we got this constraint by observing that the score, if we scale up and scale down our hyperplane, our linear hypothesis, we can get it such that the score, W transpose xn plus B, is equal to 1 for the closest point, and it is greater than 1 for the points that are not the closest. And so if that's the case for the closest point, if we multiply it by the class label, we always get a value that is at least 1. It's equality, where we get the closest point, xn, and for those points that aren't the closest, it's the greater than part. And so now we're going to convert this inequality constraint to 0 form. So we're going to subtract 1 from both sides of the inequality, and we get yn times our score W transpose xn plus B minus 1 is greater than equal to 0. So now what we're going to do is use the equality version instead of this inequality. For the closest point, we have equality, and we know because we subtracted 1, it's going to be equal to 0. Now, we use the equality version of this, and we're going to assume what we're going to call our Lagrangian slack. And so here, we're going to include a Lagrange multiplier, alpha, and we're going to have a one-to-one mapping between an alpha and each one of these in-sample points, xn. Some of them are going to be the closest, or one of them is going to be closest, or some of them will be closest to the plane, and the others will not be closest to the plane. And so this alpha is going to modulate up and down this difference between the point and the plane. And so this quantity is called the slack. And the slack is the amount that our point gives you that exceeds 0. And we modulate the slack with our Lagrange variable, our Lagrange multiplier that we introduce. And so here we have the slack, which is just a transformation of our score times the class label minus 1 to express it as an equality constraint for the smallest distance that these points can have, which corresponds to the closest point off the hyperplane. Okay, and so our slack can be exactly 0 if it's a point, the closest point off the hyperplane, or our slack can be bigger than 0. It's not tightly touching closely to the hyperplane. All right, so in our optimization problem, we're going to want as much slack as possible. And the expression for slack is always going to be positive because at a minimum it's 0, but typically it's going to be greater than 0 because not every point is closest to the hyperplane. And so what we're going to do, because this is a minimization problem, we're going to negate this Lagrange variable times our slack. And we're going to add this up for each one of the in-sample points. So we have our minus, our sum, for n goes from 1 to big N. We're going to have our alpha, Lagrange variable, for each xn, our class label times score minus 1, and this is going to be our slack. So we have our Lagrange multiplier times the slack for each one of our in-sample points. Okay, and so we have that as our objective, and what this penalty term in the minimization problem corresponds to, it says, get the classification correct, and I'm going to put it in 0 form, talking about the slack, how tight those points are in our selection to the hyperplane, while maximizing the margin, which is minimizing 1/2 W transpose W. And we're going to add them up across all the data points. And this is our unconstrained version for our optimization problem, going back to this solution that I gave at the outset. And so this involves both a minimization of some of the variables, our weight vector and our bias, and maximization of these Lagrange variables. So we have two competing forces interacting, a minimization and a maximization. Now this minimization and maximization corresponds to something called a saddle point. In a saddle point, and this is an illustration of a saddle point, it's called a saddle point because it looks like a horse saddle. And here, the saddle point corresponds to where the blue contour lines intersect the red contour lines. Now, if we look at this surface, we have two variables, this front edge going back and forth, and this other edge going front and back. Now, if we take the plane for this front face, we see that we can maximize with respect to this first variable, let's call that x1, and we can minimize with respect to this other variable, x2. Now, of course, when you maximize, that wants to pull your solution for x2 in this direction. When you minimize with respect to x2, that wants to pull the solution for x1 in another direction. Now, when you try to strike a happy medium, this point here, that's maximizing with respect to x1 while minimizing with respect to x2. You notice it's suboptimal with respect to each single variable, but it's trying to satisfy both of them. Now, that point is also what the Lagrangian is after. It's that equilibrium point, and that's what our Lagrangian optimization is giving us It's giving us these saddle points. Okay, and so we will continue on in our next module. As usual, please stay healthy, stay safe, and I'll see you all on Tuesday.